Okay, so today we're going to find the geometric mean. So first let's investigate. So what it means to be a geometric mean, let's start with the square root of a times b. But let's make sense of these numbers. Let's assume that a equals 4 and b equals 9. So if I were to say that, I would say that 4 times 9 equals the square root of 36, which is 6. So what this means, the geometric mean, it means that if you have a side that has a measure of 4 and you have another side that has a measure of 9, the geometric mean would be 6. Kind of the same idea, right? Very, very similar, right? Okay. So let's use this to find the geometric mean in a different way. Now this is what the book says. You don't need to write this down. For two positive numbers a and b, the geometric mean is the positive number x where the proportion a to x equals x to b is true. This proportion can be written using fractions as a divided by x equals x divided by b, or with cross products as x squared equals ab, or x equals the square root of ab. No, that's why I went on YouTube. Okay? So let's take what this said, what the book said, and what I just showed you, and let's blend the two. So this says the geometric mean between 2 and 50. So let's do what I did, and let's do what the book says, and then you can see how they relate. So originally I said the geometric mean is the square root of 2 times 50, which is equivalent to the square root of 100, which equals 10. Now the book's way of doing it is, if I don't know what the geometric mean is, I do know there's a relationship between these two numbers and the geometric mean. And that relationship is, everybody needs to write this, because this is the way you're going to be using it. It just didn't make sense the way a book jumped to it. Okay? So 2 can be compared to the geometric mean, and that ratio will be equal to the geometric mean being compared to the largest side. Now, if you were to do this mathematically, how would I solve this equation? Cross multiply. So I would get x squared equals 100, which is the same thing that I just did. You're going to have to do it this way. But I thought if I started here, it wouldn't make much sense. Okay? Everybody with me so far?
Wait, so why do we have to do it that way?
You're going to be applying it this way. You'll see. Okay? Questions so far? We all realize that this should be x equals plus or minus 10, correct? But are you ever going to have a negative amount on the side of a triangle? No. So it's just x equals 10. You don't have to write plus or minus. Thank you. Okay, so let's try one more. Find the geometric mean between 25 and 7. Let's just do it the way the book says now. Now, I can compare a big triangle to a small one, or I can compare a smaller triangle to a larger one, correct?
Yep.
So couldn't I still write this? 25 compared to x is equal to x compared to 7, which is x squared equals, I'm not even going to multiply these, I'm just going to do this. Isn't that still the same?
Yeah.
What? No. Because look. See what I did there?
Oh, because you cross cancel the twos?
Because 25 is really 5 squared, and you kick it out because it's a square, and the square root and a square are inverses of each other. So why multiply 25 times 7 when you can just kick the 5 out into 5 root 7? Okay. What's 5 times the square root of 7? Well, I know. What's the square root of 4? And what's the square root of 9? So isn't it going to be between 2 and 3? No, between 2 and 3. 2 point something. I'm guessing around 2.5. So what is it? Do you have a calculator? $2.6. 2.6 times 5. 13.2. The book, you can. That wouldn't be wrong. But unless it says to simplify to round to the nearest 10. But you have to multiply that by 5.
Wait, what do you mean? Divide 5 with a 10?
No. This is really saying, guys, this is really saying 5 times the square root of 7, which is 5 times what? 2.6. So when you multiply that out, you get 13 and 2/10. Okay? That's what that means. That's what this means, guys. 5 times the square root of 7. Are we okay? Okay. We're going to skip this. 13 and 2/10. What do I need to go back to? Devin, you're just sitting there kicking back, and then now you want me to go back? You need to look at your shoulder partner. Okay. This is where I need you to really pay attention, and I need to not talk over anybody, okay? There are 3 theorems in this book. There are 3 theorems in this book, and I could go straight to them, and you could write them out, and good luck to you, okay? I'm going to explain them a little bit differently. Got it? All right, so let's look at theorem 8.1. So I'm going to draw myself a right triangle. Let's make a right triangle. Here's a right triangle. I'm going to take and I'm going to turn this triangle and I'm going to put it right here, and I'm going to, so where is the right angle? On top. The only reason I turned it was so you could see that it was a right triangle, that all I did was turn it. Okay, I'm going to label this right triangle. You know what I'm going to do? I'm going to flip it around so that it looks like, sorry guys, I'm going to flip it around so that it looks like what I've got on my paper. Sorry. Let me just group these and then flip it. Didn't work. Oh, I know why, because I already had it rotated. That makes sense. I apologize. I just don't want to confuse myself. Again, so the top is the right triangle, or the right angle. All right. Let's label this. I'm going to label it A, B, C. I'm also going to draw an altitude. What can we say about an altitude? it makes a 90-degree angle. I'm going to call this angle right here D. Next, I'm going to consider the fact that in this triangle I have just created, by using this altitude, 3 right triangles. There are 3. Do you see them? And we're going to label them. And I'm going to show you. All right triangles. The largest right triangle that we started with in the beginning is a triangle ABC. We're going to start with the right angle and label from there. So on the biggest right triangle I have, what side, or I'm sorry, not what side, which vertex, A, B, or C, is the right angle? B. So I'm going to label this B. Then I'm going to ask myself, I have a longer leg. The longer leg extends to a vertex. What will we call that vertex? A, so this one has to be C. We have another triangle here. It's this middle-sized triangle right here. You see it?
Yeah.
I want to label that triangle. Let's start with the right angle again. What would we call that right angle? D. And the longest leg goes up to A. Therefore, this side is B. Do you see it? The short leg goes to B. This is the hardest part of this right now. Devin, put it away. Smallest triangle is the easiest one, right? This one is D, B, C. You don't even have to turn that one. You just got to pull it apart, make sense of it. That's the hardest part, okay? In the book, they don't pull it apart. They leave it like this, and then they talk about all the pieces of it. No, they'll say that, I'll show you right now. Okay, so we can say that triangle ABC is similar to triangle what? ADB, good job, James, which is similar to triangle BDC. In that order, unless I named this one. If I said BAC, I'd have to say DAB and DBC. Right? You have to go in the same order. That's theorem 8.1. Theorem 8.1 says that if you have a right triangle and you draw an altitude, then the 3 triangles will all be similar triangles. In so many words, that's what it says. Okay? So far, still good? Okay. Ready for theorem 8.2? All right, let's look at these 2 triangles. What do these 2 triangles have in common?
Right triangle.
Okay, they both have a right angle. True.
Same measure.
Which one? No. There's one in particular that matches.
AAB. Oh, ABC.
These 2 triangles right here. Does anybody see it? What? They both have DB. It's a little abstract. Does everybody see how they both have DB? Now, can't you see?
AB. With the first 2 triangles.
We'll get there.
Yeah.
We're talking about these 2. So let's talk about some comparisons. This one's on the bottom leg. This is the top leg. So couldn't I compare AD to DB? But if I did that, what would I be comparing on this one? BD to DC. It's almost like the transitive property. It's not, right? But it almost is. It's like you have to find the middle one. So AD is to DB. This comparison is equal to DB is to DC. Okay? That is the second theorem, Theorem 8.2. Let's look at it from this standpoint, because this is what the book does. Does everybody see how this is to this is equal to this is to this? You can see it, right? If these three triangles are similar, then always this leg is to this leg will always be equal to the measure of this leg to this leg. Okay? Let's look at it on here. On here, it would be AD is to DB is the same as DB is to BC. I'm sorry, DC. Let me say it again. This is to this is to this. Now, to me, I know that sounds simple, but when you're working with three different theorems, it can get a little complicated. I thought this was much easier. I can see this very easily. I can see this better than I can see this, especially if you took this triangle and put it upside down. Then I would be trying to figure it out. And then you add numbers to it, and you have numbers all over the place. I would much rather break my triangles apart and just say, that side looks like that side, this side looks like this side. I know the triangles are similar, therefore I can say, this is to this as this is to this. So far, so good? So let's talk about Theorem 8.3. So James, you saw another comparison between the first triangle and the second triangle. What did you see? They both have AB. AB is on this leg, AB is on this hypotenuse. All right, well, let's see how we could compare them. One has AB. They're in different spots, right? So I'm going to put them in different spots. But their comparisons are going to be equivalent. How could we make their comparisons equivalent? Where is AB on this one?
AC.
Good. Do you see it? AC is to what? AB. AC is to AB is the same as AB is to AD. Do you see it? Do they go in the same order? Hypotenuse, leg, hypotenuse, leg. See how that works? Let's look at it when you're looking. This is the harder one of the two. When you're looking at it like this, I should change my colors on this, correct? Uh-oh. Okay, this is a B. Let's change my colors to what? Red? How about green? So we said we're looking at AB, AB, and AB. So AC is to AB just like AB is to AD. AC is to AB, AB is to AD. This is how it looks on this. AC, this whole thing right here, AC is to AB just as AB is to AD. That one is confusing. Wait, it goes on. Also, you can say AC is to BC as BC is to DC. I know. That's why I separated the triangles, so you could actually see it and compare them rather than going, huh, I don't really see what they're talking about. Here's what the book says. The measure of an altitude drawn from the vertex of the right angle of a right triangle to its hypotenuse is the geometric mean between the measures of the two segments of the hypotenuse. YW, here's YW, is the geometric mean between XW and WZ. So XW is to YW, YW is to WZ. The same thing I did, only I separated my triangle. This one says YZ is to XY as XY is to XW, or XZ is to YZ as YZ is to WZ. Or you can do it my way. Okay, let's do it my way. Ready? Copy this down. We're making good time right now. Okay, so we have this figure. I am going to pull the figure apart because it's not going to make any sense to me unless I pull it apart. So I'm going to draw myself 3 different triangles. Let me copy this one, paste to paste. This one's a little bit smaller. Make this one the smallest one. Why do you have to make 3? Because there's 3 different triangles in there. Because there's 3 different sizes. Okay, so this is right angle, right angle, right angle. Let's make sense of it. Once we put numbers in here, I think some of you are going to say, oh, okay, I'm getting this now. All right, so let's label this. What is the right angle? What's this point? C? So if this is the right angle, yes, that's C. And the long leg? A. So that makes this one B. All right, smaller triangle, this middle one right here. Tall as A. The right angle is B. The other side is C. Correct. What about the smallest one? D. Tall one C. The other one C. Now let's use these numbers up here that they gave us. They said BD is 6. I'm going to label it over here. Let's change my color. I'm going to label it over here, and I'm going to label it over here. So DB is 6. And do we have any more DBs? That's the only one. AD is 27. So where am I going to put 27? I've got an AD here. Do I have another AD? No. I do not. AD is here, 27. Now you tell me. It's up to you. Can you guys see that second theorem?
Yes.
Can you?
Yes, it's 27. Well, I don't know if you're
Going this way or using this?
No,
Using this one or using this one?
I don't think. I'm just trying to measurement of ATB is similar to ABC.
Yes.
Similar to BDB.
Where am I going to put my x's? Where's the geometric mean? Hold on. Where's the geometric mean? Tell me which segment is the geometric mean. D, C, and D, C are the same, correct? Does everybody see how DC and DC are the same? So now I just set it up, right? Nope. 27 is to X is the same as X over 6. And from there, it's just X squared equals the square root of 27 times 6. Who's going to go faster than me?
Me. 12.7. 162.
The whole thing is 12.7? Is he right? He is right. You are. He already had it. Okay, it's 162. I was just checking to see if James had this done already. 12 and 7/10.
I don't know how you figure out that. How do you figure out the 12.7?
Just square root of 162. Okay, you guys ready? The other way the book tells you to do it, guys, is 27 is to DC as DC is to 6. But I don't remember that as well. I actually have to see it. I like seeing it better. Okay, you're not using your calculator right, so I can help you with that. Are you guys ready? Moving on. All right, I'm going to skip number 3 for now to make sure we have enough time. But number 3 is important, okay? So just put number 3, save some space on your paper, and let's do number 4. Here's number 4. Copy down this triangle. Okay, so let's get started on this one. Let's draw 3 triangles. I probably should make them perfectly similar, but I'm just going to do it quickly. Let me label them. Okay, my big triangle. What's this one? Tall one's L, K, J. All right, what about the smaller one, the middle one? Tall one's L, M, K. Good. And the smallest one? K, J, M. All right, let's label them with a different color. All right, so KM is 10. I have another KM right here. It's 10. Those have something in common right there. You see that? That's probably going to be that's your geometric mean right there. The geometric mean is they both match, right? So we're gonna get there. All right. So now LM. Do I know LM? LM is C. What else do I know? KJ. KJ is D. Is that about it?
And MJ is 5.
MJ is 5. There's another KJ. That's D. Awesome. Okay, so I see a relationship with these two here, and I see a relationship with these two here. So let's do this relationship first, because I see matching right there. All right, so I'm going to put a 10 and a 10, and what am I going to compare these to? C and 5, so I would put, where would the C go? C on top, 5 on the bottom. See how I set that up? I can compare this side to this side is this side to this side. So let's cross multiply. What do I get? 5C equals 100, so 1C equals 20. So this side right here is C equals 20. C equals 20. Now I have to find D now. How am I going to find D? I actually have another piece of information here. I know. It's not 5C because now it's now 25. So JL is 25. So now how am I going to work that?
25 over D.
Wait, 10 over D equals...
You don't want to have two different variables. James already had it.
Yes.
James, what did you say? 25 over D equals D over, no. Why 5? See how I did? You see it? 25, the hypotenuse is to the leg as the hypotenuse is to the legs. So 25 over D is to D over 5. Right? So now I get D squared equals the square root of 25 times 5, or 125. Got it? Which equals 5 rad 5, which is 11. I got 11.2 after I round. How you guys doing? Good? No, I wouldn't mark that off. Okay. So far, so good? Okay, let's try the last one. Let's go back to number 3. All right. No, it's not. Exactly. Positive people don't put others down. Mrs. Alspatch, I'm guessing how you say it, that's how you say it, is constructing a kite for her son. She has to arrange perpendicularly 2 support rods. So this is one support rod, this is another support rod. The shorter of which is 27 inches long. So this smaller one is 27 inches long. If she has to place the short rod 7.25 inches from one end of the long rod in order to form 2 right triangles with the kite fabric, what is the length of the longer rod? So I'm trying to find the length of the longer rod. Okay? I'm going to ignore this other information right here because I don't really want to look at it. It's just confusing me. I'm sorry? It makes it easier, doesn't it, the technology? Okay, so now I have this triangle, so I'm going to draw myself 3 triangles. Let's label them. The largest one? Oh, let's label it first. A, B, C, let's call this one D. So the largest one is what? C, C, A. Okay, middle one? C, B. That's the one, it's a big one. Yeah, this is the smaller, the middle one right here. And this small one is the easiest one. That's D, this is B, and this is A. All right, let's label it. This whole thing was 27, and it told us that they were congruent. So what's 27 divided by 2? 13.5. So that makes this 13.5. It also makes this 13.5. We already have a geometric mean right there, and I don't even have anything else done. Yep, because they're both dB. So if you label them, you already just figured it out without even having, you label it first, and then you figure out what the measurements are later. So what is AD? 7.25. Do I know any other ADs? Nope, that's the only one. All right, so let's make a comparison. What are we going to compare? Let's set it up first. 13.5, 13.5. What am I going to compare? X is to 13.5 as 13.5 is to 7.25. Put this in my calculator. I'm going to get 7.25x equals, what is it? What's 13.5 times 2? I'm sorry. Times 13.5. 182.25. Divide that by 7.25. What do you get? X equals 25.1. So X is CD, which happens to be right here. I just got my answer. Didn't it want to know this? It wanted to know the length of the longest rod. How do I know my answer now?
You gotta add them,
Just got to add them. Was it really that hard of a problem? So my answer is what?
32.4.
Thank you. Inches.
That's not even that hard.
No, you just have to piece it apart, make sense of it, plug in your numbers. All right, good job, guys.